All right, good morning, everyone. As we have been introduced, we are the team Acere. The title of our paper is Analysis of Alternative Energy Sources, Storage, and Transmission for Cuba's Infrastructure. My name is Antonio Diaz. I'm the team leader for this project, and I'm currently a junior in Mechanical and Aerospace Engineering.
My name is David Cabrera. I'm also a junior in Mechanical and Aerospace Engineering.
My name is Andrea Coman, and I'm a sophomore in Chemical Engineering. Okay. And our missing member is Gabriel Tanquero, and he's a junior in Material Science, but he couldn't be here today. So a viable energy infrastructure is necessary for the efficient functioning and development of a country. And in recent years, Cuba's national energy consumption has skyrocketed, which has really emphasized their need for a sustainable and domestic energy source. So our first slide shows the Antonio Guterres.
I can't hear you talking. Turn on. I think the mic is the mic on.
I thought so.
You just speak a little louder.
Closer? Okay. So the first slide shows.
Take it in your hand.
In the hand?
There you go.
Okay. The first slide shows the Antonio Guterres power plant, which is a thermoelectric plant in Cuba. And it's currently being retrofitted to burn natural gas instead of the traditional domestic heavy oil. And this conversion represents Cuba's instability with its fuel resources. Currently, the infrastructure is based on 11 such thermoelectric plants, which most of them are 25 years old. They're a little inefficient, and they run only 60% of the time. So the country's current energy staple is fossil fuel, which is a very reactionary resource. The supply is always controlled by a changing group of countries, and the prices are volatile. At the moment, Venezuela is subsidizing Cuba's fuel imports, but the political nature and the possible depression of the crude oil market puts the relationship at risk. So in the 1970s, the national electricity system was installed, which attempted to connect the country through one large electrical grid. However, it's a very centralized system. You can tell from the image. Most of the power plants are located in one area, and if one of them fails, the rest of the country is prone to blackouts. And also, the transmission grid suffers a lot of energy loss because of the old technology and poor design involved in building it. It also loses energy in the long power transfers and illegal connections to the grid. So in the 21st century, there are frequent power plant failures, which, especially during the peak demand periods. And this spurred the Cuban government to introduce the energy revolution, which emphasized energy conservation and promoted alternative energy resources for the country. So part of the energy revolution involved installing small generators, several thousand small generators throughout the country, and small fuel oil plants to help distribute and decentralize the energy. So currently, Cuba has 40.5% of its energy distributed, and which helps it better handle interrupted transmission. The energy revolution also replaced all the inefficient appliances in houses and altered the residential electrical rates to encourage conservation. However, as you can see from this graph, Cubans are already very conservative with their energy. The per capita energy use is much lower than the US. So the issue isn't with further conserving energy, but with actually implementing a stable domestic energy resource. So we're proposing an alternative energy plan that's focused on such distributed generation. So we looked at 4 primary energy sources, and we used decision matrices to standardize our thought process and funnel our options down to find the most suitable fit for Cuba. So we looked at hydropower, sun, solar energy, wind energy, and biochemical. So hydropower has the strongest foundation in Cuba. It's their oldest alternative energy source. The usable potential in the country is relatively low, although there is a potential for 650 megawatts of hydropower energy. Most of the potential has already been utilized, or the remaining areas are naturally sensitive areas that are environmentally protected. So in hydropower, we're basically already taking full advantage of those sources. Cuba also has experience in biochemical energy. They have traditionally converted sugarcane residues into thermal energy, known as bagasse. But this form of energy is very dependent on agricultural output, so it's not very stable. And its role as a domestic energy source has declined since the 1990s when the economic crisis hit. And the amount of land that could be used for cultivation has decreased greatly from 20% to barely 5%. So it's very limited for expansion. We also looked at solar energy, which Cuba has great resources in, and it's also decentralized, which is a plus because we want something that can be distributed throughout the grid and help in case of a power plant failure to keep energy available. So solar would be dependable for that, but its capital investment cost makes it unsuitable for Cuba. So this is an example of a rural school where solar panels were implemented to help distribute energy. So the last resource we looked at was wind, which we found that Cuba had recently invested heavily in and received very promising returns. And there are currently 3 main wind farms in Cuba that are holding the wind capacity.
All right, so from the history and the research we did on Cuba's current infrastructure, we learned about 3 main criteria that we can use in our design. We learned that a decentralized approach works well. It helps prevent mass failures, and it distributes the power throughout Cuba. We also learned that reducing intermittency is very important, especially for alternative energy sources such as solar and wind. Those sources tend to be inconsistent. The sun isn't always out, the wind isn't always blowing, and we need to figure out a way to solve that before Cuba could depend on that to a greater extent. The third thing that we learned was that there's an abundance of untapped wind energy. Cuba just recently has invested in wind energy, and they've received promising returns. However, it still doesn't make up a large majority of their total energy production. As you can see in this map, Isla Juventud has a very good source of moderate winds on land and would make for an excellent pilot program to any introduction of new wind energy for testing and prototyping on Cuba. This is a graph of the installed wind capacity in Cuba through time. It's very recent, but it steps up as they install new wind farms. It's very similar to this graph, which is the graph of wind turbines in Denmark. And Denmark serves as a good example for wind energy because of the world. They have one of the highest percentages of dependence on wind energy. They are currently producing 28.2% of their total generation comes from wind energy. However, they're having the similar problems that the rest of the world is having with wind energy. It's very intermittent. It's not consistent, and you can't rely on it. So if you see, they're saying they have a capacity of this many megawatts, yet their actual generation throughout the year is this blue line, which falls well below their installed capacity, and it's mostly due to that intermittency. So ways we could solve this intermittent issue is we can take advantage of optimal wind power and height. These maps are satellite images analyzing the best locations for having 95% consistency of reaching around 0.2 kilowatt per meter squared around Cuba. This map also shows the optimal height, and around Cuba it's blue, which is 1 kilometer height is the optimal height for wind energy. And reaching that's very difficult to do with traditional wind turbines because it's limited to its central post. So another way to solve the intermittency issue is having an energy storage system. Whenever you're producing surplus amounts of energy, you can store that surplus instead of selling it to another nation or just not using it. And it pretty much averages out your energy gathering throughout the day and throughout the year. This storage system specifically is hydrogen storage. It works by using an electrolyzer, which splits the hydrogen and oxygen atoms of water using electricity that is surplus from what we generated from wind turbines. This is actually an example from a project in Acere, Norway. The whole island is completely dependent on wind energy and storage into hydrogen. So that system will be combined with a new form of wind turbine, which is called the Aerostat wind turbine. This wind turbine is very adaptable. It can be deflated and is portable, so it can be moved around throughout Cuba. So whenever there's a hurricane or any issues like that, it can be put away, it can be protected, so they don't have to over-engineer their wind turbines to withstand those types of forces. It's a floating wind turbine, so it depends on some type of lifting gas. Typically, it would be helium. However, 75% of the world's helium actually comes from the US, and that really limits Cuba. So our way around that is to use hydrogen, which would be supplied from the hydrogen that we produce in our hydrogen energy storage system. So they couple very well. This is our prototype model that we designed. This is assembly of the model. It has an axle to reduce stresses on the actual skin of the blimp, as shown here. And these are individual hydrogen cells so as to isolate any failures. And these are our 5 kilowatt generators. This is a close-up of the 5 kilowatt generators I've just been showing. It has its individual gears, which increase the rotations per minute coming from the blimp to a ratio of 1 to 25. So what the actual 5 kilowatt generator receives is a much higher RPM, which leads to much more efficient energy gathering. This is what we designed specifically with a hydrogen Aerostat wind turbine in mind. We have vents on the top to relieve any heat created from the generator, and we isolated all the components from within the generator from the blimp so that if any hydrogen leaks were to occur, they would not have contact with the generator, hence eliminating any most possibilities of any sparks transmitting and possibly causing a failure. This graph here is a very complicated Ashby plot, but we used this to figure out what materials we wanted to choose for the skin of our aerostat. We wanted the outside to be UV resistant, so we used a material called Tedlar, which is a polymer. Polymers fall within this range, which is a good balance of density to strength. We also used Mylar in the inside to reduce diffusion of the hydrogen, and it's also heat resistant in case there's any type of incendiary. And then for the middle layer, we used a tension specific polymer to hold most of the load, and it's known as Dacron. And here's a cost comparison of a hydrogen storage system. What we will be using specifically is a hydrogen combustion turbine. As you can see, it has an average cost of 19 levelized cost per kilowatt hour. This is estimated for a 3 to 5 year future time frame. And it compares very well to other forms of energy storage, such as batteries. Batteries tend to be a lot more expensive. However, they do have the benefit of higher efficiencies.
This is a cost analysis of our design compared to other 10 kilowatt alternative energy sources. As you can tell, our prototype ranges between $13,000 and $15,000 US, which is it's pretty good compared to other traditional alternative energy sources. Since we did say that Cuba's main problem was financial stability and initial cost, I think this is pretty good. Another problem that traditional wind turbines have is maintenance cost. Traditional wind turbines are higher than 50 feet high. So what ends up happening is that you need really specialized people to work on these wind turbines when something does break. Another issue that arises is that these wind turbines are not mobile. So if there's a lightning storm or a thunderstorm, damage can be caused to these really massive and expensive blades. So whenever something does happen to these blades, they're first off really expensive and really hard to replace. The way we combat this with our prototype is by having it be able to descend. So whenever something does happen to our prototype and it requires repair, the maintenance cost is relatively cheaper, since we could just descend it and pretty much patch it up. A problem that most wind turbines have is that it's kind of like a Pandora's box. It looks great at first, but then a lot of problems arise. One of these problems that arises is many deaths of flying creatures, such as birds. So what ends up happening with birds is that the blades might not look like they're spinning really fast at the center, but the tip of the blades actually go really fast. And birds can't see these blades rotating. So they get hit by them, and you have estimated between 10,000 to 40,000 fatalities of birds and bats. The problem that happens with bats is that whenever the blade passes through the center axis, it compresses air. And this air compression, when a bat passes by a wind turbine, it kills the bat. It explodes their lungs. So this slide shows failure of a traditional wind turbine in high winds. What happens here is that the brakes, the emergency brakes, fail due to really high winds in the storm. What the dangers of this are is the massive pieces of really heavy equipment falling everywhere. They might cause damage to property, or they might even injure people. We combat this by having our blimp just descend if something does happen. So the area that's affected is much smaller. It's pretty much just the dimensions of the blimp. And most of this damage could be avoided by just simply lowering the blimp when unfavorable conditions show up. So Cuba plans on expanding their wind farms. So currently this isn't a problem. But if they do expand and they get more wind turbines, such as in Denmark, a problem that arises is sound. When wind turbines, when the blades passes by the center axis and the air gets compressed, it actually releases this really high-pitched sound, which can be heard over a very long distance. So currently that's not a problem in Cuba, since they only have 3 wind farms. But if more wind farms are added, this sound can disrupt both human and environmental. It could cause environmental problems. Besides, it's kind of discomforting being able to hear this really annoying sound from really far away constantly. Another problem that arises from traditional wind turbines is that you need a really large base in order to hold the massive center pole and eventually the blades on the top. What happens is that they're permanent. So once you modify the landscape for it, it's stuck and you can't do anything with it. Since our prototype doesn't need a base, it just needs a place to be attached to, this wouldn't be a problem, which is very eco-friendly. Another problem that happens is that the base is all filled with concrete, which releases a lot of emissions. As we can see from this chart, wind energy is actually one of the least it releases the least emissions out of all energy sources, which makes it very eco-friendly. So what ends up happening is that a lot of people have this notion of the Hindenburg incident. And whenever we say that our blimp is going to be filled with hydrogen, this is the first thing that comes to mind. What ended up happening in the Hindenburg was that the coat of paint used in the exterior was flammable. So when a spark happens, and the flammable oxide just kind of encourages the fire to happen. But research here at the University of Miami has shown what happens when hydrogen does catch on fire. To the left, you have a car that runs off hydrogen catching on fire. Since hydrogen is the lightest gas, it just flies really high up, really fast. So it's really hard for the fire to spread vertically. Versus normal gasoline car just pretty much explodes. So since our prototype has many ways to combat this fire or leak, our design is fairly safe. And even if something does happen, the fire would just rise up instead of making the whole balloon explode. So this comes to emissions. Emissions from our blimp would just be hydrogen. Hydrogen is not bad for the atmosphere, and it won't cause any sort of problem.
So in conclusion, we propose the flying wind turbine as a cost-efficient and reliable form of distributed energy and storage. And we expect a lot of future improvements to make themselves evident as time goes on in both the function and the reliability of the design. And we also want to point out that Cuba's energy problem cannot be resolved with just one or two resources, but through a carefully designed combination of several. And our proposal just presents what we believe to be one integral part of such a combination. And there are possible ramifications in the future for a hydrogen economy. So surplus hydrogen that is produced can be traded to other countries or used in other parts of the infrastructure, such as transportation in Cuba. So it provides a lot of opportunity for Cuba's energy infrastructure.
Thank you.
All right, we're ready for the question session.